Morning, all of you. In this session, I am going to explain about design procedure of boiler joints. It is related to riveted joints unit number 3. This is the example figure for a boiler. A boiler has a longitudinal joint as well as circumferential joint. Okay, this is a longitudinal joint. This is a circumferential joint. Okay, the boiler has a longitudinal joint as well as a circumferential joint. Okay, so you can observe here. This is the complete shape of a boiler. Okay, this boiler has longitudinal joint. Okay, longitudinal joint as well as circumferential joint. The longitudinal joint is used to join the ends of the plate to get the required diameter. Okay, so this is the diameter of the boiler. To get the required diameter of the boiler, we are using longitudinal joint for join the ends. Okay, this is the end. You can observe this is the end of the plate. Okay, for this longitudinal joints, we are using 2 cover plates. Okay, for joining the ends, we are using top and bottom cover plates. Okay, this is a top cover plate, this is a bottom cover plate. Okay, these are the rivets. Okay, now this is a circumferential joint. The circumferential joint is used to get the required length of the boiler. Okay, to get the required length of the boiler. For this purpose, the lap joint with one ring overlapping the other alternatively is used. Okay, I will explain again. Longitudinal joint is used to join the ends of the plate to get the required diameter of the boiler. Okay, for the you can observe this is the shape of a boiler. Here, this is the joint. Okay, so for join the end of this boiler, we are using inside cover plate and outside cover plate. Okay, for riveting purpose. Okay, these are the rivets. Okay, now this is the top view of a boiler. Now I will show the isometric view. Okay, so here this is the actual boiler. Okay, this is the joint. For join the this end of the plate, we are using bottom and top cover plates. Then after we are riveting. Okay, these are the rivets. Okay, this is the isometric view of a joint. Okay, this is the longitudinal butt joint. Yeah, this is the butt. Okay, this is the butt. Okay, along the length of the boiler, we are riveting to join the butt. Okay, to join the ends of the boiler plate. Okay, now circumferential lap joint. The circumferential joint is used to get the required length of the boiler. Here, this is the half. For example, this is a boiler. Okay, this length is not suitable for entire boiler. So we want, if you want to extend this height, then you have to join another cylinder. Okay, Now here this is the joint. Okay, this is the joint for these two cylinders. For making leak-proof joint, we are making a circumferential lap joint. Okay, for connecting these two cylinders. Now these are the rivets. Okay, so this is the top here from this view. That is the side view of the joint, circumferential joint. Okay. Okay, the circumferential joint is used to get the required length or required height of the boiler. Okay, for this purpose, a lap joint with one ring overlapping the other alternatively is used. Okay. What are the assumptions made in design of our boiler joints? The following assumptions are made while designing a joint for boilers. The load on the joint is equally shared by all the rivets. Okay, the load on the joint is equally shared by all the rivets. The assumption implies that the shell and plate are rigid and that all the deformation of the joint takes place in the rivet themselves. The tensile stress is equally distributed over the section of metal between the rivets. You can observe this diagram. Okay, the tensile stress is equally distributed over the section of the metal between the rivets. Okay, this is the rivet. These are the tensile forces acting on the plates. Okay, the shearing stress in all the rivets is uniform. Okay, shearing here. This rivet may fail due to shearing off here. Okay, the crushing stress is uniform. There is no bending stress in the rivets. Okay, that means there is no bending load acting on the rivet. The holes into which the rivets are driven do not weaken the member. The rivet fills the hole after it is driven. The friction between the surfaces of the plate is neglected. Okay. Now these all are assumptions for designing the boiler joints. Now recommended joints for pressure vessels. The following table shows the recommended joints for pressure vessels. You can observe this table. Okay. If the diameter of the boiler is 0.6 to 1.8 meters and thickness lies between 6 mm to 13 mm, then you have to use double riveted joint. Okay. Now, if the diameter of the boiler lies between 0.9 to 2.1 meter and the thickness of the plate is 13 mm to 25 mm, then you have to use triple riveted joint. Okay. If the diameter of the boiler shell lies between 1.5 meters to 2.7 meters and the thickness of the shell plate lies between 19 mm to 40 mm, then you have to use quadruple riveted joint. Okay. So these are the recommended joints for design of boilers. Okay. Now the design Now I will explain about design procedure of a longitudinal butt joint for boilers. Already we discussed earlier. There is a longitudinal joint. Okay, so here you can observe. Now I will explain how to design this longitudinal joint. That means selection of butt straps and selection of a proper diameter of a rivet. Okay, diameter of a rivet, thickness of a plate, thickness of a boiler shell. Okay, thickness of a boiler shell, thickness of a butt strap. Okay, diameter of a rivet and margin. Okay, margin and distance between two rows of rivets, that is back pitch or row pitch, and pitch of the rivets. Okay, I will explain how to determine pitch of rivets, row pitch, thickness of a butt strap, okay, thickness of a boiler shell, diameter of a rivet. Okay, I will explain one by one. Okay, first, now here this is the butt joint. Okay, the distance between rivet, nearest rivet to the joint is margin M. Okay, minimum distance is margin M, and the distance between two successive rivets, the distance between two successive rivets is pitch, pitch of rivets. Okay, the distance between two successive rivets is pitch. This one also pitch, P. Okay, here from here to here, pitch. Okay, now this is the one row of the riveted joint. Okay, and again this is the another row of the riveted joint. Now the distance between two successive rows of rivets, two rows of rivets is called row pitch or back pitch. Okay, and this is the thickness of the shell or boiler, thickness of the boiler plate. Okay, so first you have to select a suitable thickness of a boiler shell, T. Okay, and these are the thickness of the butt straps or cover plates, thickness of cover plate, that is denoted by symbol T1. Okay, T1 is the thickness of the butt strap, okay, this is the thickness of the shell, this is the thickness of the butt strap. Okay, and here this is the diameter of the rivet. From here to here, this is the diameter of the rivet, that is small d. Okay, diameter of the rivet, small d. Okay, this is margin M. Okay, this is the pitch P. Okay, now I will explain how to determine a suitable thickness of the boiler shell, thickness of a butt strap, margin, diameter of a rivet, and pitch. Okay, row pitch. I will explain one by one. First, according to the Indian boiler regulations, IBR, according to Indian boiler regulations, the following procedure should be adopted for the design of longitudinal butt joint. Okay, here I am going to explain about the design procedure of a longitudinal butt joint. Longitudinal butt joint for boilers. Okay, you have to follow IBR, that is Indian boiler regulations. Okay, for design of boilers, you have to follow IBR rules, that is Indian boiler regulations, Okay. Yeah, the first step. In first step, you have to select a suitable thickness of the boiler shell plate. Okay, thickness of a boiler shell plate. So here small t. Small t is the thickness of the boiler shell. Okay, already we know the subject, that is the strength of materials or mechanics of solids subject. Okay, already we discussed about thick cylinders and thin cylinders topic. Okay, so this is the formula for thin cylinders. Okay, circumferential stress. Already we know the formula for circumferential stress. Circumferential stress for thin cylinders, sigma c equal to pressure, inside pressure in the cylinder, and mean diameter of the cylinder or inside diameter of the cylinder divided by 2 into thickness of the cylinder. Okay, this is the formula for circumferential stress. Circumferential stress for thin cylinders. Okay, this formula is used for circumferential stress or hoop stress for thin cylinders. Okay, thin cylinders, for thin cylinders. Okay, here P is the maximum inside gas pressure. Okay, maximum inside fluid pressure. D is the inside diameter, internal diameter of the shell. Okay, now T is the thickness of the cylinder. Okay, sigma C is the circumferential stress. Circumferential stress in boiler material. Okay, from this formula we can determine the thickness of the cylinder. Okay, so that is the thickness T equal to PD by 2 into sigma C. Okay, so here same this formula I used for design of boilers. Okay, so here T is the thickness of the boiler and P is the maximum inside gas pressure or maximum pressure inside of pressure. D is the internal diameter of the boiler. Okay, 2 into sigma T. Here sigma T is the permissible tensile stress. Permissible tensile stress. Okay, so that value also equal to circumferential stress. Okay, and here this is the joint efficiency, longitudinal joint efficiency. Okay, zeta L. Zeta L is the longitudinal joint efficiency. So here zeta L is the longitudinal joint efficiency. Plus you have to consider corrosion elements, that is 1 mm for corrosion elements. Okay, so this is the formula for thickness of a boiler shell. Okay, this is the first step. By using this equation, you have to find out a suitable thickness of the boiler shell. Okay, this is step number 1. Okay, now the thickness of the boiler shell should not be less than 7 mm. Okay, for design of boilers, the thickness of the boiler should not be less than 7 mm. Okay, this is very important point. And another point, the efficiency of the joint may be taken from the table. You have to take a joint efficiency from this table. For a single riveted butt joint, you have to consider 45 to 60% efficiency, joint efficiency. Maximum efficiency is 63.3%. Okay, for double riveted butt joint, 63 to 70% is the joint efficiency, longitudinal joint efficiency. and 77.5 is the maximum joint efficiency. Now, for triple riveted butt joints, the efficiency is 72% to 80%. Okay, lies between 72% to 80%. Maximum efficiency is 86.6%. Okay, these are the joint efficiencies. For lap joints, sorry, these are the lap joints, these are the butt joints. Now these are the factor of safeties for boiler joints. Okay, always you have to consider above 4 for factor of safety. Okay, always you have to consider factor of safety above 4. So these are the estimated factor of safeties. For lap joints, you have to consider 4.75 for hand riveting. For machine riveting, you have to consider 4.5. Okay. For single strap butt joint, you have to consider 4.75 for hand riveting, 4.5 for machine riveting. For single riveted butt joint with 2 equal cover straps, you have to consider 4.75 for hand riveting, 4.5 for machine riveting. For double riveted butt joint with 2 equal cover straps, okay, 2 equal cover straps, then you have to consider 4.25 for hand riveting, 4.0 for machine riveting. Okay, these are the factor of safeties for longitudinal butt joints. Okay. Now, in second step, you have to determine a suitable diameter of the rivet. Okay, small d is the diameter of the rivet. This is the formula for diameter of the rivet. D equal to 6 root t. D equal to 6 root t. Okay, so this formula is applicable when thickness of the boiler shell is above 8 mm. Okay, if the boiler shell thickness T is above 8 mm, then you have to consider this formula. Okay, but if the thickness of the plate is less than 8 mm, then the diameter of the rivet hole may be calculated by equating the shearing resistance of the rivets to crushing resistance. That means you have to equating the formulas, that is shearing strength PS equal to crushing stress. Oh, sorry. Shear stress equal to crushing stress. Shear strength PS equal to crushing strength PC. Okay, by using this relation, you have to find out the suitable size of the rivet. Okay, you have to find out the suitable size of the rivet diameter. When thickness of the rivet, sorry, when thickness of the plate, riveted plate, is less than 8 mm. Okay, if the thickness of the plate or boiler shell is less than 8 mm, then you have to use this relation. Okay, if the thickness of the plate is above 8 mm, then you have to consider this relation. Okay, these are the standard rivet diameters. Okay, for rivet hole diameters. Here 12 mm is the basic size. Here these are the basic sizes of rivets. Okay, these are the rivet hole diameters. Okay, so here you can observe a small clearance we have to provide for rivet and rivet hole. Okay, 12, 14, 16, 18, 20, 22, 24, 27, 30, 33, 36, 39, 42, 48. These all are standard rivet diameters. Okay, and these all are the standard rivet holes. Okay, 13, 15, 17, 19, 21, 23, 25, okay, 28, 31, 34, 37, 41, 44, 50. These all are the standard rivet holes. Okay. Now, in third step, you have to determine the suitable size of the pitch. Suitable pitch of rivets. Pitch means the successive distance, the distance between two successive rivets. The distance between two successive rivets is called pitch of rivets. Okay, the distance between two successive rivets is called pitch. Okay, here pitch of the rivets should not be less than 2D. Okay, which is necessary for the formation of head. The maximum value of the pitch of rivets for a longitudinal joint of the boiler as per Indian boiler regulation. Indian boiler regulation is P max equal to C into T. C is the constant value. This value may be taken from table number 9.5. T is the thickness of the boiler shell plus 41.28 mm. Okay, this is the maximum pitch. Okay, here these are the values for a constant C. For lap joint, for single riveted lap joint, you have to consider C equal to 1.31. For double riveted lap joint, you have to consider 2.62. For triple riveted lap joint, you have to consider 3.47. For a quadruple lap joint, 4.17. Okay, these all are the values for constant C. Okay. Now, for single riveted butt joint, single strap butt joint, you have to consider 1.53. For double riveted single strap butt joint, 3.06. For triple riveted single strap butt joint, 4.05. Okay. In similar way, single riveted double strap butt joint, 1.75. Double riveted double strap butt joint, 3.50. Triple riveted double strap butt joint, 4.63. Quadruple riveted double strap butt joint, 5.52. Okay, so these all are the constant value. Okay, now in step number 4, you have to determine the suitable distance for back pitch or row pitch. PB is the back pitch or row pitch. Okay, the distance between two successive rows of rivets is called back pitch. Okay, the distance between two successive rows of rivets is called back pitch or row pitch. Okay, so this is a value for back pitch 0.33 into P plus 0.67 D for zigzag riveting. Here P is the pitch. Okay, D is the diameter of the rivet. Now 2D, 2 into D for chain riveting. Okay, back pitch. These all are the values for back pitch. Okay, now 0.33 P plus 0.67 or 2D. Okay, now these are the values for butt straps, thickness of the butt straps. Okay, the thickness of butt strap in no case shall be less than 10 mm. Now T1 is the thickness of the butt strap. T1 equal to 1.125 into T, 1.125 into T for ordinary single butt straps. 1.125 T into P minus D by P minus 2D for single butt straps. Every alternative rivet in our outer rows being omitted. Okay. Now T1 equal to 0.625 into T for double butt straps. That means double cover plates of equal width having ordinary riveting. Okay, chain riveting. T1 equal to 0.625 T into P minus D by P minus 2D for double butt straps of equal width having every alternative rivet in the outer rows being omitted. Okay, so these all are the thickness of the butt straps. Okay, for unequal width of butt straps, the thickness of the butt strap or T1 equal to 0.75 into T. For wide strap on the inside, T2 equal to 0.625 into T. For narrow strap on the outside. Okay. For determining the suitable size of margin, suitable distance for margin, you have to consider M equal to 1.5 into D. 1.5 times the diameter of the rivet for margin. Okay, these all are the important steps for design of longitudinal joint for boilers. Okay. Now coming to the, so here this is the diagram for longitudinal and circumferential joints. Yeah, this is the length of the joint. So this is the longitudinal joint and this is the diameter. Okay, so this is circumferential joint. Okay. Now design of circumferential lap joint for boilers. Okay, so here these are the boilers. Circumferential joint is used to get the required length of the boiler. Okay, so this is the circumferential lap joint. These are the rivets. Okay, these are the important steps for a design of circumferential lap joints. In first step, you have to determine suitable thickness and diameter of the rivets. Okay, so for determining the thickness of the shell and diameter of the rivets, you have to consider same procedure as a longitudinal joint. Okay. In second step, you have to find out number of rivets required to circumferential joint. Yeah, this is the formula for determining the required number of rivets. Okay, here n is the total number of rivets required to make the circumferential joint. Okay, this is the formula for shearing strength of the rivets. Shearing strength of the rivet. Okay, PS is the shearing strength or shearing resistance. Okay, n is the total number of rivets. 5/4 d square. 5/4 d square is the cross sectional area of the rivet, and tau is the shear stress induced in the rivet material, or shear stress induced in the rivet. Now WS is the shearing load, total shearing load acting on the circumferential joint. Okay, WS is the total shearing load acting on the circumferential joint. That value equal to pi/4 d square into P. Maximum, yeah, you can observe capital P is the maximum inside pressure. Yeah, this value is the maximum inside gas pressure, gas or steam. Okay, pi/4 d square, capital D. Capital D is the internal diameter of the boiler shell. Okay, internal diameter of the boiler shell. So this is the cross-sectional area or inside pressure area. Okay. Now by equating this equation 1 and equation 2, you will get the value of n. Okay. Pitch of rivets. This is the formula for determining the efficiency, circumferential efficiency of joint. Okay. If the efficiency of the longitudinal joint is known, then the efficiency of the circumferential joint may be obtained. Okay. So here it is generally taken as 50% of tearing efficiency in longitudinal joint. But if more than one circumferential joint is used, then it is 62% for the intermediate joints. Okay. Now, Zeta C is the circumferential lap joint efficiency. Circumferential lap joint efficiency. Okay. Now, P1 is the pitch of the rivets. Pitch of the rivets for lap joint. Okay. P1 is the pitch of the rivets for lap joints. Okay. Now, D is the diameter of the rivet. Okay. Now, from this equation, we have to find out the suitable value of P1, that is the pitch of the rivets, pitch of lap joint. Okay. Now, this is number of rows. Fourth step is number of rows. The number of rows of rivets for circumferential joint may be obtained from the equation. Number of rows equal total number of rivets divided by number of rivets in one row. Okay. So here capital D is the internal diameter of the boiler shell. Capital D is the internal diameter of the boiler shell. Small d is the diameter of the rivet. Okay. Now PB is the row pitch. Okay, M is the margin. Okay. So the values are same as longitudinal joints.